Hello everyone. Welcome to Security at Scale, how Goldman Sachs manages network and access control. My name is Harsha Sharma. I'm a solutions architect at AWS. Joining me today presenting this session is Robert Cossin, who is a vice president at Goldman Sachs, and Sujoy Saha, who is an associate at Goldman Sachs. As our customers are growing and expanding their footprint on AWS, the number of accounts that they're managing and creating is increasing. A key consideration as a byproduct of this that our customers have to make is around how do they manage network connectivity across their accounts, not only on AWS, but from on-premises to their AWS accounts as well, keeping fine-grained access control in mind. AWS provides options via services such as AWS Direct Connect, VPC peering, VPC sharing, and our customers always ask us what's the best option for them at scale, keeping their security posture and requirements in mind. In this session, Robert and Sujoy will cover how Goldman Sachs went through this problem and how they managed to reach an ideal solution that fits their requirements and how they implemented and managed this at scale via their automation. In today's session, we'll begin with who Goldman Sachs is and the teams Robert and Sujoy represent. We'll then go into the core security tenets of the transaction banking business at Goldman Sachs, and we'll see how that lays the foundation for all the design patterns that they've built. We'll then see the initial approach that the TxB team took, which is to run all their applications in a single large AWS account, and we'll see how that did not align with their core security tenets. This then led to the creation of their transaction banking micro account approach, and we'll go into the details of that as well. We'll then focus in on connectivity, and we'll see how the transaction banking team achieves cross-account connectivity across their micro accounts and on-premises to AWS connectivity to their micro accounts. In both of these scenarios, we'll look at how they achieve this at scale and how they manage this via their automation. Finally, we'll look at the lessons that the Goldman Sachs team learned through their journey of implementing all of this. With that high-level overview, I will now pass on to Robert and Sujoy to take you through the rest of this talk.
Thanks, Harsha. Goldman Sachs is a leading global investment bank. I'm on the transaction or TxB team. Sujoy is on the core cloud engineering team. Transaction banking is a new business at Goldman Sachs that's cloud native and provides cash management services to other corporations. Core engineering manages AWS usage for TxB and more broadly. These are some common components that are found in a commercial bank. Let's go through a use case. Let's imagine Corporation A, who has an account in TxB, wants to pay Corporation B. They'd submit a payment request through an API, web, or a file. Payment orchestration picks up the request and decides how we'll manage it. It will then pass it to validation screening to ensure that the payment is valid, legal, and it'll check for the ledger for balance or a credit limit. And then it'll finally pass it to a payment rail, or what I have labeled as outgoing incoming payments, which will actually send the payment into the world. We will come back to this slide in a few minutes. So let's talk about our core security tenets. Our primary goal here is to establish security in layers to ensure that an issue in one layer won't cause a compromise. So starting at the bottom, we already established zero trust at the application layer and we encrypt all communication. We use AWS policies for all of our Amazon resources, and for our own processes, we use mutual TLS, where each process specifies the allowed certificate names from which it will accept connections. It's also important to add network controls on top of our application controls to ensure a safeguard in case of a mistake on the app layer. We purposely separate perimeter and network access from network controls on the top of our tenets to focus on the advantage of the VPC border. Also, note that with a focus on security, it's absolutely crucial to think about developer experience. Specifically, our goal is to make it easy for developers to do the right thing. So let's talk about our initial approach. Initially, everything was in one account. So if you look at this picture, it's the same components from before, right? And the developer life seemed really easy, right? All you needed to do was you deployed your infrastructure to one account, you passed around DNS names, and you passed around your certificates, and you were able to make everything work. So the expected flow here would be the green arrow. And how could you prevent the red arrow from taking place? Specifically, where the web connects to the payments, where the web connects to the payments without going through orchestration and validation. So we already talked about how we have the application security, and we could use security groups to prevent the red arrow from happening. But because everyone's in the same account, what happens if somebody in that account misconfigures it? That was a pretty big risk on our part, and we were concerned about it. Also, what other issues can result from co-tenancy? So back to the prior side, managing security groups and NACLs is complicated. On top of that, co-tenancy causes a lot of resources to be in the account, and that introduces management challenges. And so we've hit many limits. We've hit limits for EC2 instances, load balancers, you name it. We've hit limits for IAM roles, right? And this became an operational challenge. Also, within an account, AWS policies have to be super granular, right? And as you get more granular, it's easier that you can possibly make a mistake, right? So the next slide will explain. Before we go into policies, let's just talk about identity versus resource policies, right? There's two main types of policies in AWS. There's resource policies, which are defined on certain AWS resources, and you can specify which IAM roles have access to which actions on those resources. And there's IAM, or identity policies, which are defined per role and define the resources and actions that that role can access. They're complementary. And so within the same account, with the exception of KMS, if you have an allow in one of the two, so if you have an allow in the IAM or in the resource, access is allowed, right? And why is this important to talk about when we talk about security? Let's go through an example. So let's imagine I have a Lambda. The Lambda is called simple Lambda. It's in green there on the bottom. And I've created a resource policy for that Lambda to allow the invoke Lambda role to access the Lambda, right? If I'm looking at it clearly, I'm saying, okay, well, invoke Lambda is the only thing that can access this Lambda, right? And actually, I could be wrong because somebody else could create an IAM policy for a new role that also includes in the IAM policy access to sample Lambda, right? And you know, with different teams in the same account, it's actually really hard to get this right, right? And how do you control this? One way to do it is you add deny statements to every resource policy. So you grant access to the roles you want access to, and you deny for all other roles. And at scale for all resources, it's difficult to get this right every single time, right? And that comes back to a point that I made a little bit earlier, which is that if you're in different accounts, this is not the case anymore, right? You actually have to be very intentional for policies to work cross account, right? So if you want to have account A perform an action on a resource in account B's resource policy must explicitly include the role in account A, and account A's IAM policy must explicitly include the resource in account B, right? So this actually happens to complement our network perimeter bias, right? Because we, as before in our security tenets, we talked about how the network perimeter is the top tier. So this led us to think about our micro account approach. So as we just discussed, the account is a natural isolation boundary, both in terms of network connectivity and policy management. So using separate accounts provides strong controls to minimize the blast radius, right? And so the logical way to maximize the blast radius in our situation was to separate each of our services into their own account, right? And now that we've done that, right, there's a lot of things we have to think about because you're no longer in one account. So we had to think about making everything easy for developers, right? Otherwise, they weren't going to use it. So we had to give them an easy way to run a container. So we gave them an ECS cluster. We needed to give them a way to get certificates so they could talk to each other, right? We needed to give them the ability to create IAM roles easily, right? And the way we did IAM was we used policies where the developers are not able to create policies. We create curated IAM policies, and developers can only attach them, right? Once we have all of that, right, now they're in different accounts and they have to be able to connect between accounts, right? And because this used to be easy, now it's a lot harder. And so there's two common paths. The first one was managed streaming with Kafka. And the second one is direct TCP connections using REST, right? And we'll go into details on that in a moment. Before we do that, it's important to talk about how we manage all of these accounts. So imagine I have an application and each application gets its own set of accounts, one per environment. So if you look on the screen here, we have one for development, one for system test, and one for production. And if you scale that out to tens or even over 100 applications, you get to having hundreds of accounts. And so how do we keep track of them? We have this on-prem inventory management system. And from our perspective, the main purpose of it is that it tracks application plus environment to and from the AWS account. And we're going to see why this is really important in a few slides. So now we got this nice account, and the developers have everything they need. It's easy to build their application, and we had to decide how to actually make the connection between accounts. And so in order to figure out how to do this, we considered the following four things. We thought about CIDR management, or IP range. We thought about account and VPC limits, network connectivity and scope, and connection initiation direction and policies. So first things first, all of these different strategies, if you're in different accounts, solve the policy problem because of what I said before. As for the network flow direction, peering was the thing that came to mind first for most people. And it's the most well-known, but it's bidirectional, which means that you can initiate a direction in a TCP connection in either direction, right? Transit gateway is similar, and it gives you additional facilities to restrict communication. And both peering and transit gateway require careful CIDR management because you can't have overlapping IPs that are peered or connected via transit gateway. VPC sharing solves the problem of CIDRs because you only have one VPC, but you still run into resource limits because you're in the same VPC. So that left us with private link, and we liked it because it's similar to our zero trust model on the application, meaning it requires bilateral agreement to establish a connection. The service has to safe list the client accounts, and then the client has to request a connection explicitly to the service account. And also, it's very fine-grained in terms of the connection, and it's only one direction, which means that the client can only connect to the service, not vice versa, and the breadth of the connection is only to resources that are behind a network load balancer. So here's a crash course in private link for people who aren't familiar. I have a service account on the right and a client account on the left. The service account would create an NLB for the service they want to expose. They attach an endpoint service to the NLB, and they specify the availability zones they want it to be available in and the allowed principals to establish which IAM roles are able to create a connection. Amazon then gives you a service name, which is for all intents and purposes a GUID. You pass the endpoint service name to the client. The client then specifies the endpoint service name on their end, and either all or a subset of the availability zones. Amazon will then create an ENI, or Elastic Network Interface, in the client account. The client then accesses the ENI, and in turn the network load balancer and everything behind it, as if it was in one network, right? And just note that on the client side, you can also add security groups on top of the ENI to control access. So how do we use endpoints in TxB? So earlier in the presentation, we spoke about zero trust at the application layer. We use PCA, or Amazon's Private Certificate Authority, to create certificates, and each service in our ecosystem has to bind to a certificate. So we create a certificate, we create a secret in the service account, in this case the ledger account, that holds the private certificate, and ECS will pick up that certificate and bind it to the process on startup, right? So once we have that, we have to establish a TLS connection from the client to the service. And there's an interesting complexity here, which is that the client side has to have a DNS name that matches the certificate name on the service. And when you create a when you create an endpoint in Amazon on the validation screening account, that endpoint is going to have an AmazonAWS.com, service GUID, AmazonAWS.com DNS name, and that's not going to match. So what we ended up doing is we use convention. And so what we do is we normalize all the certificate names on the services to use a specific VPCE DNS zone. Let's say it's vpce.txb.gs.com. And then all of our client accounts will always have that DNS zone. And when you create your service, you specify a DNS record that points to the ENI that will point to the ENI. Right? Another challenge is zonal alignment. So if you have the validation screening account and the ledger account being different accounts, the different availability zones are different. So what I mean by that is US East 1A in the validation screening account won't necessarily equal US East 1A in the ledger account. And so to manage that, we had to handle, we had to pass around physical availability zones, right? So all of this together means that we have a client. The client has to create a DNS record that connects to an ENI. The ENI connects to the endpoint service, and it has to match the certificate on the service side, right? And so the first cut of this was the service team would manually set up allowed principals, right? They would then manually email, the service team would then email the service name, the certificate name, and the physical AZs to the clients. The clients would store that in their Terraform code, and then we go ahead and they would build things. And there was a couple of problems with this. The first thing was just keeping them in sync, right? If the service made a change, they would have to often, email the clients. Secondly, there was a control problem. The valid principals list being manually entered meant that it was hard for us to guarantee that prod clients didn't connect to non-prod services and vice versa. And also, it was even potentially possible to connect to accounts outside of GS. And so, because of all of this, because we wanted to add to improve the developer experience and add controls, we needed to do something better. And so we came out with our VPC endpoint management strategy. And we established the concept of a logical endpoint service, which has a friendly name. So the friendly name maps to a VPC endpoint GUID. It also maps to the certificate name and the availability zones as we were passing around before. Right? The logical endpoint service name is actually the same for each application environment. So if I have a service called the ledger service, which is what I'm exposing here on the right, that service would just be called ledger service. And it's up to the endpoint management service to manage which environment you're in. And that solves a lot of problems, right? So you can no longer connect outside of your environment. Also, on top of that, we use the inventory management system that we spoke about earlier to ensure that a given account knows what lane it's in, and it only allows connections to accounts within GS. What do I mean by that? It means that when you're creating your safe list or your allowed principals, you specify application names and not account numbers anymore. And so you don't have the ability to create any safe lists that exist for, You don't have the ability to create safe lists that include accounts that are not in GS, right? So let me just walk you through a quick use case. There's a ledger service that wants to create an endpoint service to be connected to by the validation and screening account. So it goes to the inventory management. The first step for the project is that it would go to the inventory management system to determine the environment that it's being built in based on the AWS account. So it would use that mapping from AWS account to application/environment. Based on the environment and the application names provided for the allowed principals, it'll derive the account numbers. It'll then create an endpoint service and write the registration file to S3 that includes the certificate name, the logical name, the certificate name, the physical availability zones, etc. Then when the validation screening account wants to connect, we're on the left side of the document now, left side of the slide right now, number 5, we would go to the inventory management service to determine the environment of the account that it's connecting to. So we know, okay, we're development. Then it would go to the inventory management repository, the registration bucket on the bottom, to determine the application environment. Then based on that environment, it would determine the service name, the DNS records, the physical AZs, and the SSM parameters. And then it would create all resources accordingly, right? And for a specific example of where we did this at scale, there's another session called ANT 305 where some of our colleagues, Venkat and Araf, will talk about how we did this to share MSK across accounts. That's really interesting. So as you can see, adding all this on solved our control problems, and it made developers' experience really easy. So all they have to do now from the server side is list the accounts the application that they want to be able to connect. And from the client side, they only have to list the logical service name. Now I'll hand it over to Sujoy to talk about how we do this for connectivity to on-prem. Thank you.
Okay, thanks, Rob. Hey, everyone, this is Sujoy, and I work in the public cloud engineering team here at Goldman Sachs. And today I'll be talking about how we are connecting to our different endpoint services from our on-premises. To start with, when we started looking into how we could achieve connectivity with our remote application VPCs, we initially thought of using AWS Transit Gateway or AWS Direct Connect to achieve this and peer our on-premises network with that of the application VPCs directly. The challenge with this, though, was that GS AWS organization has over 100 AWS accounts, which meant that for every single one of the VPCs in those accounts across multiple regions, we would have to extend our on-premises network onto those different VPCs, which would include doing subnet management, network routing, managing route tables, And the whole process was very time consuming and had a lot of overhead, which application teams typically did not like. The other alternative was that we go over the internet and connect with their VPCs directly. The challenge with that was that we were deliberately now introducing weak security into our environment, which was something we couldn't stand for. So we decided instead to use a transit VPC, which would interface our on-premises network with that of our application VPCs, which would in turn help us achieve complete control over ingress and egress flows originating from from our on-premises network into our AWS environment, as well as by having the transit VPC construct, we would move away the control function of the different application teams from managing networks. This would be managed by the cloud engineering team in the central core engineering function, and it would be offered as a platform for different application teams to onboard to. And finally, we would achieve a strong separation of application VPCs from the GS network, which we shall see in this overview. Here, we have an overview of the GS Transit VPC that goes over the entire flow, starting from on-prem and ending at the application VPC. In this, the Transit VPC is a central hub and spoke network where we are leveraging the use of private link to connect different applications that are hosted in different app accounts, and then making that available as individual spokes to this central hub account, and making that hub account itself be available to the rest of the GS environment, which is located over here. Now, as you can see with this particular model, we are baking security as well as the strong network boundaries and segmentations into this flow. None of the application accounts share a network. The transit VPC is the only network that is paired with the on-premises environment. And if for whatever reason a application account were to be compromised, or like a VPC or the network were to be compromised, all we would need to do is we would need to terminate the VPC endpoints that link the application account with that of the GS Transit account. Now, from the application team's perspective, what does this mean? All they would need to do is deploy their applications into their ECS or AWS Fargate constructs or EC2 instances, and then set up their private link constructs on their side. This includes setting up the VPC endpoint service, the network load balancer, and point that to the appropriate application targets. Now, once they have that set up, all they would need to do is provision the VPC endpoint in the transit VPC, and then set up a friendly domain name that they can use to resolve from on-premises, as can be seen over here. One additional step that they need to function is to open firewalls that exist between the GS on-premises network and that of the transit VPC. This firewall protects the firm from the rest of the external environment, and AWS is considered to be such an environment, right? And all approved flows need to be basically go through some review process to open the firewall so that they can connect with the app. Now, even though we've got strong security now, the app team has to configure 3 different resources to connect with their application post-deployment. So we decided to build out quite a bit of automation to make this very easy from the developer experience perspective. Here we have the process outlining the flow of automatic VPC endpoint provisioning. As part of this, the application team uses Terraform modules that helps them construct the intent to connect with their deployed application services. And they can use things like CloudFormation or infrastructure as code modules that they can use to define that. Now, as part of this, the application team will construct the VPC endpoint service, network load balancer, and appropriate application targets for their side of the private link. And then they'll define a custom SRV record that will help define their connectivity intent. As part of this, they'll declare what is the application's friendly domain name, the ports, the availability zones, as well as the VPC endpoint service that identifies their particular application. Now, the SRV record will be used to identify their connectivity intent. This means that if a user is creating a VPC SRV record, this means that they are creating a new VPC endpoint. If they're updating fields inside the SRV record, that means that they're updating the VPC endpoint, such as they're adding a new port to it, or they're to a security group, or they're adding a availability zone and expanding the number of ENIs that are available to endpoint. If they want to delete the VPC endpoint, all they need to do is delete the custom SRV record. Now, as part of this capturing this user intent, we are using the event bridge service to capture these different user interactions and pass that along to our VPC endpoint provisioning step functions. Over here, we have the flow diagram that showcases this entire flow. Now, whenever we receive a new VPC endpoint request, we shall evaluate it to validate if the request is compliant with our security standards and that the GS organization, the account that is requesting it, has a good standing within the GS organization. Once the validations are passed, we'll go ahead and honor that request. Let's take an example here and say that we are provisioning a new endpoint. So once we create the VPC endpoint, we'll also create a DNS alias for that. Now, in addition to serving as a DNS alias, we create this entity called a service alias that uniquely maps each connectivity request. This specific alias can be seen over here. It's called service1.region.account.gs.com, where region and account are determined at runtime, and service1 is a construct that is configured by us, right? And this specific service alias remains constant throughout the entirety of the connectivity request from the user. Now, be it either like create, update, delete, any function. Now, this service alias and the other connectivity components for the VPC endpoint are tracked in inventory. So we'll insert that into our DynamoDB table, which will track this information going forward. And then after that, we'll take the service alias and register that with our on-premises firewall manager that will open up connectivity on our firewall that exists between our transit VPC and that of our on-premises network. Now, Goldman Sachs has built out quite a very good platform for managing connectivity between different systems and services. As part of this, all a user needs to do is maintain a Git repository where they give information about the different services and systems they want to connect to, and then indicate the ports and other details that they want to, so that the system can then open firewalls between them. As part of this specific use case, we ask the user to open firewalls between their host on-prem and that of the service alias, and give the port information so that they're able to request that. Now, in this example, we can see that the user has said, give host A access to my service, the service being service1.region.account.gs.com on a specific port. They'll submit this as a merge request to the overall project that, as I said, manages the entire firewall connectivity. At this stage, the security analyst team gets to review their changes, and then this is their opportunity to validate if the application that's deployed in AWS is actually meeting certain application security standards, and then validate that, and then after that, basically go ahead and approve that. Right now, in case they don't have, they're not following those security standards, they can always reject that request. In which case firewalls are not opened. But if they do, they can go ahead and approve the firewall change, and then that will indicate that at some point of time, the firewall manager will go ahead and open up the firewalls thus opening up connectivity from the on-premises host A and to that of the service one that's on the transit VPC. And ultimately, this in turn opens up connectivity to the remotely deployed application. Now that the user has gone through a process of opening firewalls, right? How do we manage changes in those firewalls? Say, for example, you have a VPC endpoint that's in transit and the IPs have changed because you've re-provisioned it or you've requested for an additional availability zone. In cases like those, where you have either moved VPCs or you've re-provisioned the VPC endpoint, IP changes can actually break your firewalls. So we capture those specific flows and make sure that from the user's perspective, that doesn't break, right? So here we have an example where the app owner has a specific endpoint, and then it has a specified set of IPs. If the VPC endpoint service is deleted and recreated, IPs have been changed to this new set. And they change because AWS reassigns them whenever new endpoint is provisioned. Now, as I mentioned earlier, we have this VPC endpoint inventory where we are tracking all these different endpoints that are being provisioned, as well as manage the current state of that, right? So we'll actually see an event coming in which has updated the IPs associated with a VPC endpoint. Now, we'll capture this as part of DynamoDB's event stream. So we have event streams turned on for Dynamo, and we are capturing those on premises, where we have a stream events processor that's iterating over all the events that we are receiving, capturing the latest events, and then processing those and sending out requests to on-premises firewall software-defined network system that basically goes in and updates those firewalls to all associated rules that are using those firewall constructs. That way, the service alias is adjusted in place without the developer having to go through a process of requesting a manual firewall change, waiting for a week, and waiting for a specific change window to take place. This actually significantly reduces the time taken to change firewalls as well as improves developer experience quite a bit. So throughout the course of this section of the talk, we've shown how a application owner or developer can request connectivity to their deployed app, as well as manage that connectivity's lifecycle through a custom SRV record themselves, and then go through a process that reviews the security of the application, as well as by baking that into this process and achieving connectivity at the end of it. If connectivity changes, they can use this process to make changes accordingly. With that, we come to the end of today's session. But before we go, let's take a look at some of the lessons we learned throughout the course of that. So in the lessons learned section today, we'll see how the fact that account boundaries and the use of AWS private link strongly improves security posture, especially if you're using the micro account model. The only problem is there are quite a few challenges that we've solved, right? And in order to for us to make sure that these challenges are not pushed to the developer and they have to deal with all sorts of problems, we had to basically make sure that we are using we are providing reusable infrastructure as code modules that the developer can take advantage of. And by automatically using them, they would inculcate good user behavior and adopt the best security practices, right? Now, by using these specific modules, they would automatically be aligned with the smoothest development path possible, as well as by using these processes, they would minimize the time that they spend on infrastructure deployment and connectivity deployments, and rather spend more time on things that they're actually important for them, such as application dev. Now, as you can see, we've used automation throughout to ensure that that we are able to bridge the gap wherever possible, and then using that has gotten us quite a bit of good results, especially from a developer experience perspective. One thing I should finally mention, though, is that by allowing business units to experiment and innovate within certain guardrails, allows them to find interesting use cases, as well as build interesting platforms, such as the one built by Transaction Banking, where they've been able to maximize the utilization of a micro account model and reduce the pain for working on those environments. And with the feedback that they've provided us, core engineering team has been able to build in similar models that will be used strategically across the firm. So we would like to say that it's been a great collaboration, and we would like to see more people adopting this model, where business unit teams go on, build their own thing, and then work with the core engineering team to make sure that they're matching the firm's security standards, as well as the core team building out a platform that others can utilize, and make sure that everyone is automatically aligned with the firm's security posture. With that, we come to the end of today's talk. I'd like to thank everyone who attended this live stream. I also want to thank Kai Huang and Joel Brown, whose contribution has been invaluable to this project, as well as other folks who are involved in both of our teams. Please make sure to complete the session survey. Myself and Rob will stay on for any questions on the live stream. Thank you so much.